Let's continue and have a look at some of the notation that we use when we're dealing with sets. So we usually use capital letters to denote the actual sets themselves. Okay, so you can think of these capital letters as being an alias for the set, a name that we're putting on the set. And typically we could use lowercase letters to denote the actual elements of the set. So the lowercase letters represent the elements of the set. So perhaps A represents a person, B perhaps might represent a number, and so on. Now, in English, we would say an element A belongs to a set, and would actually write it out as indicated in the slide here. In mathematical notation, to actually state this in a succinct manner, we would write the following. A, and then we've got the symbol for element, sort of like an epsilon symbol, and then the actual set itself, S. So we would read this as A is an element of the set S, or A is a member of the set S, or A is in the set S, or S contains the element A. Now, when it comes to actually specifying the elements of a set, again using mathematical notation, we have a number of ways of doing this. So one way to specify a particular set is to list all of the elements. Okay, so this is known as roster notation. So for example, here we have the set S equals, we've got a curly brace, then we list the elements of the set, A, B, C, D, and E in this case, and then we close off with a curly brace at the end. So what this is saying is that we have a set S, and the elements of this set are A, B, C, D, and E, whatever they represent. Okay, so the elements of the set are separated by commas and enclosed in these curly braces. Now, there's a couple of things to note about sets as well. The order in which the elements are listed is not important. So in this case, we have A, B, C, D, and E listed in that order. But equally, we could say that the set S is the elements B, A, D, C, and E. So the order is not important. One other point to note as well is that we don't list an element twice in the same set. So we wouldn't have A, B, B, C, D, and E. Okay, so the idea here is we want to extend this idea of a set even further. So we've seen that a set is a collection of well-defined objects. We'll just extend that a little bit further to say that a set is a collection of well-defined, distinct objects. And all that means is that we don't have duplicates in the set when we're considering the elements. Now, the roster notation or the list notation for sets is convenient if we're dealing with a set with a small number of elements, or if we're dealing with a set where there is a sequence of elements and it is easy to determine what the other elements of the set would be given a particular sequence. But in many cases, it's going to be difficult to list out all of the elements, especially if we're dealing with a set with a large number of elements. So for example, a set with 10 million elements, it's going to be quite onerous to actually list out all of those 10 million elements. So we'd like some other means of specifying what the elements of a set should be. And one of the ways we can do that is by using a property notation, or also called a set builder notation. And in set builder notation, what we do is specify a property associated with all of the elements in the particular set. So in the example we have here, we've got a set S, and we're saying that S contains elements X, and then we give a property for what all of these elements would have. So S is the set X, such that X is an integer and X is greater than 100. Okay, an integer is one of the numbers 1, 2, 3, 4, 5, 6, and so on. 0 is included in the integers as well, and all of the minus whole numbers. So minus 1 would be an example of an integer also. Okay, so in mathematical notation, we have S equals curly brace X. The bar symbol is read as such that, and then x is an integer and x is greater than 100. Okay, so to read that completely, we'd have S is the set of all x such that x is an integer and x is greater than 100. Okay, so in this case, the integer is greater than 100. There's an infinite number of them, but using this notation, it's quite a succinct way of actually specifying all of those elements that should be contained in this set. Okay, this bar character is read as such that. Now there are many sets that we will encounter, but some of the sets that we will typically encounter have to do with numbers. And we have different types of numbers that we will consider. So the first set that we probably encounter growing up is the set of natural numbers. Now these are also called a set of counting numbers. So it's represented by a symbol of a capital N, and really the set of counting numbers are 1, 2, 3, 4, and so on up to infinity. Okay, so we're actually writing it out here in list notation, but because it's a sequence that's easily identifiable, we can use the 3 dots, the ellipses, to indicate that the numbers continue in the sequence in the fashion dictated. Okay, now the set of natural numbers will not be capable of dealing with all of the types of numbers that we need to consider. So if we take 2 natural numbers, for example, let's take the number 2 and the number 3. If we add those 2 numbers together, we get 5. So 2 plus 3 is 5. And 5 would also be a natural number. So in this case, we would say that the natural numbers are closed under the operation of addition. However, if we take into account the operation of subtraction, and we say 2 minus 3, well, we end up with minus 1 in that case, and we see that minus 1 is not an element of the natural numbers. Okay, so we need to extend out our idea of number to the set of integers. And in this case, we have included 0 and all of the negative numbers. So the set of integers, represented by this capital Z symbol, coming from the German Zahl for number, will give us all of the negative numbers, 0, and all of the positive whole numbers. Okay, so we can see that the set n is actually part of the set of integers, those positive numbers. In somewhat a similar fashion, we can add 2 integers and we'll always get an integer. So for example, minus 1 plus 1 is 0, and 0 is in the set of integers. We can also subtract 2 integers and get another integer. So minus 1 minus 2 is minus 3, and that's also an integer. So the set of integers is closed under the operations of addition and subtraction, and also multiplication. So multiplying any 2 integers will always result in another integer. So minus 1 multiplied by 2 is minus 2, and minus 2 is an integer also. So the set of integers is also closed under the operation of multiplication. However, if we consider the operation of division, we will find that we can come up with ratios that won't have a representation in the integers. Okay, so we need to extend out our idea of number even further. So for example, 2 divided by 3 would give us 2/3, which is not an integer. So to extend out our idea of numbers, we introduce another set, the set of rational numbers. Okay, and this is represented by a capital Q, standing for quotient. And the set of rational numbers is the set A divided by B, or A over B, such that A is an element of Z and B is an element of Z, with the restriction that B is not equal to 0. Okay, so division by 0 is not allowed. And we can see that the set of rational numbers in some way includes all of the integers, and in doing so also includes the natural numbers. So for example, the integer 3 we could represent that as a rational number as 3 over 1. Okay, so is this the extent of our number system? Will this include all of the numbers that we have to deal with? The answer is no. Okay, so we also need to consider numbers that cannot be expressed as a fraction. Some examples of such numbers would be pi and the square root of 2. And there are infinitely many numbers, such as these numbers, that cannot be expressed as a fraction. So they are not elements of the set Q. Okay, and these numbers are called irrational numbers. If you're interested in some history behind the irrational numbers, please check out the following Wikipedia link that might be of some interest. Okay, so we recognize that the irrational numbers need to be included also in our concept of number. So when we take the rational numbers and the irrational numbers together, we end up with the set of real numbers represented by capital R here. So the real numbers is the set X, such that X is either a rational number or X is an irrational number. To represent the real numbers graphically, we can think of them as points on a straight line, points on a continuous straight line. So if you were to draw a straight line without taking your pen off the paper, this would give us a graphical representation of the real numbers. And we have to imagine that it extends in either direction out into infinity. So the real numbers include the irrational numbers, they also include all the rational numbers, and in doing so they will include all of the integers and all of the natural numbers also. So for example, to represent the square root of 2 on the real number line, we would see that it's represented by a single point positioned between the integers 1 and 2. So there are some other questions regarding sets that we would like to find an answer to. Okay, so we've just seen that a set doesn't list the same element twice. Okay, so let's do some examples just to clarify the situation. Okay, let's consider some objects again, and this time we'll consider some numbers. Okay, so let's consider the numbers 1, 2, 3, and 4. And this time we'll collect them together as such. So let's put the number 1 down twice, and then the number 2 and the number 3. So the question is this a representation of a set? And we would say no. And the reason for that is that we've listed the number 1 twice. So for a set, we don't include the same element twice within the set. So this would actually be an example of what is called a multi-set. Okay, so within maths we have the idea of a multi-set in which you can list elements more than once. Okay, but for sets, what we would consider is 1, 2, and 3. Okay, the collection of objects or numbers 1, 2, and 3. This time we don't actually list the same element twice, number 1.